In this video, I'm going to be doing the solutions to the make-believe fields sample problems. This video is going to be on the solutions to the sample problems with make-believe fields. So question 1, I'll assume you've already read all of it and have thought about it. So I'm going to just go onto the solution here. I'll start with the free body diagram of the cell phone. The cell phone has a mass of 250 grams. So there's going to be a force of gravity of m times g, so 0.250 times 9.8. And I'll get that number in a sec after I grab a calculator. But there's also a new force now, this make-believe force, due to the lithium field. And if you read the definition of the lithium field, it applies 35 newtons per gram of lithium. 35 newtons per gram of lithium. So the force is going to be 35 times however many grams of lithium there are, which in this question it says there's 2.2. Okay, so this one, I don't need a calculator, it's 77 newtons. The other one, actually, I probably don't need one either. That'll be 2.45 newtons. So there is a net force pointing up. 70 newtons is way bigger than 2.45 newtons. So I can get the acceleration with Newton's second law, the net force divided by the mass. So the net force will be 77 take away 2.45. And the mass of the phone is 250 grams. If you think it's 252.2 grams because you added the 250 with the 2.2, I'd still accept that because, the wording's not too specific. I think either of those can be assumed. But I'm going to use 250 as my mass. I'm going to get out a calculator. And actually, it should be 0.250 because Newton's second law, the mass should be in kilograms. So this gives me an acceleration, very large, 298.2 meters per second squared, which can be used to solve what the question is asking, which is to find the final velocity after it hits the ceiling. So it's going to rise up by a displacement of 2 meters. So it's like a multi-part question. Now we have a kinematics section where we have a displacement that's going to be 2 meters up. The acceleration is 298.2 meters per second squared up. We are starting at rest, and we have to find out the final velocity. So you have to go all the way back to kinematics. I'm just going to write out the equation that's going to work out. One term is 0, cross it off. Looks like I just need to square root this. And we shall put that in the calculator, giving me 35 meters per second when rounded to 2 significant digits. And do not worry, as the definition of the lithium field says, the ceiling is padded, so your cell phone is not going to break even though it hits it at 35 meters per second. Question 2 is the same question. We're going to solve it again, but using the conservation of mechanical energy. You may have noticed when we did energy way back when, we could solve a lot of the same problems we solved as dynamics, just in a different way. And that's what we're going to do with this lithium field. So we know the gravitational potential energy formula is mgh. Now this question provides us with the new potential energy. this new make-believe potential energy associated with the lithium field, and the formula is given there. Okay, so we are simply going to apply the energy before equals energy after. Now, I guess a little bit of a review, I can write every single energy down, but I added the lithium as well. It's probably a little overkill because there's no spring involved. Like, there's no reason to write spring potential energy. Okay, the object starts at rest, so the kinetic energy is 0 at the beginning. And if here's the table with the cell phone, and here's the ceiling, it's a 2-meter difference. I can set my reference height wherever I want, so I'm going to set it at the table. Okay, I'll set the reference height at the table, so the object has 0 gravitational potential energy at the beginning. And finally, you need to read the words carefully. In this new make-believe potential energy formula, y represents how far below the object, below the ceiling the object is. Y is always a positive number. So what it's saying is that y equals to 2 when it's on the table, but when it hits the ceiling, y equals to 0. Okay, that's how far below the ceiling it is. So it will equal to 0 when it hits the ceiling, meaning there's actually going to be no lithium potential energy when it hits the ceiling. So we are down to 3 terms. It starts off with lithium potential energy, and all of that is going to be transformed into gravitational and kinetic energy. So substituting with the formulas, you use the formula given for this make-believe field, and mgh for gravitational potential, and half mv squared for kinetic. Now, be careful with the m's. There's 2 different m's. The normal m, is the mass of the phone. Whereas the m with a lowercase, the subscript of L, is the mass of the lithium. Okay, so we actually cannot cancel these m's out because they are 2 different m's. Okay, so what we do is we solve for v, the speed. So to solve for the speed, the first thing I will likely subtract mgh. Then I'll multiply by 2, divide by m, and square root. So that will look like this. Multiply by 2. Divide by m, square root. And we have the values of all of those. So we have 35 times 2.2 times 2 minus 0.25 for the mass of the phone times 9.8 times 2 as well. The height is 2 at the ceiling. And divide all that by 0.250, and hopefully we get the same answer as we got in the previous question. So this will take a while for me to type out. and I got 35 again with this. So that works out. There you go. So just like real life gravitational fields, gravitational potential energy, you get two of the same answers with dynamics and with conservation of energy. You can do the same thing even with these make-believe fields. As long as you make up your field that satisfies the criteria that I gave in the assignment, then I should be able to build this potential energy formula for you so that you can solve the problems that you're going to be getting. Okay, so there was a second make-believe field given in the examples in the assignment outline. It was the one that repels mosquitoes. So here, this question, again, I'll have to assume you've read it. Find the acceleration of the mosquito. So this is a dynamics question, find the acceleration. Acceleration is net force divided by mass. It says that gravity is going to be negligible. This mosquito is very, very light. So this force from this device, this make-believe device, is going to be way stronger than the force of gravity on the mosquito. So it's going to be negligible. Okay, so the force, let me go back to the definition of this Anopheles repellent. Okay, so it says that the field created by this device will equal to 5 times 10 to the negative 6 over r squared newtons per microliter of mosquito saliva. Okay, so that many newtons per microliter of saliva. So the force is going to be this field times however many microliters of saliva there are. Okay, so A is how many newtons per microliter of saliva. So we multiply that by how many microliters of saliva the mosquito has. You're going to get something in newtons, which is the force. All right, so in this question, the distance the mosquito away is 2 meters. Don't forget to square it. And the number of microliters of saliva is 1.8. So when I calculate that out, that will give the force. I mean, I won't do that just yet because the acceleration is going to be the force divided by the mass. So, I mean, it's just going to be the same thing as above with the mass in the denominator as well. So I'll just put it all together. So the mass of the mosquito is 5 times 10 to the negative 6. Oh, wow, I chose nice numbers. There's 5 times 10 to the negative 6 on the top and the bottom. So it's really just 1.8 divided by 4. 1.8 divided by 4. I think that's 0.45. Double check. Yep. Okay, so that'll be the acceleration of the mosquito, and this will be away from the device. The device repels it. Okay, so that's kind of a weak device. I'm gonna need someone to build me a stronger one, because that's a pretty low acceleration. So this last one here, With the fictional field that repels mosquitoes, if your field satisfies all the criteria in the assignment, I should be able to build you a potential energy formula associated to your field. So this is the potential energy associated with the field for this mosquito repellent. And this is going to be a conservation of energy question. So you have the device here. You have the device. And then mosquito will start here, 1 meter away. It's at rest. And we turn on the device, it's going to repel the mosquito away. And the question is, how fast is it going once it has been repelled to 2 meters away? Okay, so this is going to be a conservation of energy formula. And again, we're assuming, as per the previous question, that gravity is negligible. So we're not going to include gravitational potential energy. There's no springs involved here, so we're not going to include elastic potential energy either. So it's going to be this new make-believe potential energy and kinetic energy. Okay, those are the only two energies involved. And this begins at rest. So it begins at rest, the kinetic energy is 0. And this is what we're left with. So I'll fill in the formulas. So we'll use the formula provided for potential. S stands for how much saliva the mosquito has. R stands for how far away the mosquito is from the device, so I need subscripts of 1 and 2 for 1 meter away and 2 meters away. And then kinetic energy is half mv squared. All right, so it's just rearranging for V and solving. So the first thing will be to subtract. So this term I'm underlining, subtract it on both sides. And when you subtract it on both sides, you'll notice that both terms have the same numerator of 5 times 10 to the negative 6s. I'm actually going to common factor that out. And we'll be left with 1 over r1 minus 1 over r2. That'll end up having me have to type in less things into the calculator. Last question, I rearranged everything first. This question, I think I may put in numbers a bit earlier to keep things a little neat. So I'm going to put in the saliva value of, this time it's 2.0. I'm going to put in the R1 value, 1 meter. And put in the R2 value of 2 meters. So I'm actually just going to calculate out the left side first to help keep things a bit neater. I am kicking myself right now. Because of the numbers I chose, it just turns out to be 5 times 10 to the negative 6. Okay, so the s equals to 2, and the 1 minus a half is a half and 2 times a half is 1. It all cancels out, and the answer is just 5 times 10 to the negative 6. I did not think about, I just kind of randomly picked these things, and it just turns out lots of things canceled out in the last couple of questions. Okay, so the mass of the mosquito is, doesn't say. So let's just assume it's the same as the, nah, let's give it a different mass, or else things will just cancel out. Okay, so this question was missing the mass of the mosquito. Let's add it in. I'll let this one be 6 times 10 to the negative 6. Okay, so we rearrange things. Square root is involved, so I'm just going to, well, the 10 to the negative 6's cancel out. So it's really just going to be 2 times 5 divided by 6 square rooted. Okay, that gives me 1.3 meters per second. So these numbers turned out to be not bad. Like they're not going to annihilate these mosquitoes. They're just going to kind of gently nudge them, keep them away from me. So I like that. I like that. All right. So there you go. This is kind of what you can expect when we get around to part 2 of your assignment, but you are working on part 1, which is due this Friday.